The strategy used in the superposition theorem is to eliminate all but one source of power within a network at a time, using series or parallel analysis to determine voltage drops and/or currents within a modified network for each power source separately. Then, once voltage drops and/or currents have been determined for each power source working separately, the values are all superimposed on top of each other, added algebraically, to find the actual voltage drops or current drops with all sources active. Let's look at our example circuit and apply superposition theorem to it. Since we have two sources of power in the circuit, we will have to calculate two sets of values for voltage drops and/or current drops. One for the circuit with only the 28-volt battery in effect, and the other for a circuit with only the 7-volt battery in effect. When redrawing the circuit for series parallel analysis with one source, all other voltage sources are replaced by wires or shorts, and all other current sources with open circuits or breaks. Since we only have voltage sources or batteries in our example circuit, we will replace every inactive source during analysis with a wire. Analyzing the circuit with only the 28-volt battery, we obtain the following values for the voltage and current. Analyzing the circuit with only the 7-volt battery, we obtain another set of values for voltage and current. When superimposing these values of voltage and current, we have to be very careful to consider polarity, voltage drop, and direction for electron flow, as the values have to be added algebraically. With a 28-volt battery, the voltage in R1 is a voltage drop with 24 volts. With the 7-volt battery, the voltage in R1 is a voltage gain of 4 volts. Adding them, we will have the voltage with both batteries, so 24 volts minus 4 volts is a 20-volt voltage drop. With the 28-volt battery, the voltage in R2 is a voltage drop of 4 volts. With the 7-volt battery, the voltage in R2 is another voltage drop with 4 volts. Adding algebraically, we get the voltage with both batteries. The voltage in R2 is 4 volts plus 4 volts, which is an 8-volt voltage drop. With the 28-volt battery, the voltage in R3 is a voltage drop of 4 volts. With the 7-volt battery, the voltage in R3 is a voltage gain of 3 volts. Adding algebraically, we get the voltage with both batteries. The voltage in R3 is 4 volts minus 3 volts, which is a 1-volt voltage drop. Applying these superimposed voltage figures to the circuit, the end result looks something like this. Currents add up algebraically as well, and can be either superimposed as done with the resistor voltage drops, or simply calculated from the final voltage drops and their respective resistances, I equals V over R. Either way, the answers will still be the same. Here I will show the superposition method applied to the current. With the 28-volt battery, the current through R1 is a current drop of 6 amps. With the 7-volt battery, the current in R1 is a current gain of 1 amp. Adding algebraically, we get the current with both batteries. The current in R1 is 6 amps minus 1 amp, which is equal to a current drop of 5 amps. With the 28-volt battery, the current through R2 is a current gain of 2 amps. With the 7-volt battery, the current through R2 is a current gain of also 2 amps. Adding algebraically, we get the current with both batteries. The current through R2 is 2 amps plus 2 amps, which gets us a current gain of 4 amps. With the 28-volt battery, the current through R3 is a current drop of 4 amps. With the 7-volt battery, the current through R3 is a current gain of 3 amps. Calculating algebraically, we get the current with both batteries. The current through R3 is 4 amps minus 3 amps, which is equal to a current drop of 1 amp. Once again, applying these superimposed figures to our circuit, the circuit will look like this. So here we have an example. Using this circuit, we have to find I of X, which is this current over here. First, let us find the current through the 3 ohm resistor with only the 12 volt battery. So we could redraw it as follows. Now, applying the superposition theorem, we need to simplify the circuit so that we can look for I. It's called the current I sub 1. And since we found the equivalent resistance, we can now solve for the current passing through that resistor. Since we found the current already, and since they are in series, they're connected in series, the current will stay the same. But we are looking for the current passing through the 3 ohm resistor and not the 1.875 resistor. So, since the 1.875 resistor is composed of 2 parallel resistors, namely the 3 ohm resistor and the 5 ohm resistor, and in a parallel circuit, what is constant is its voltage. So voltage is equal to current times resistance. Voltage is equal to 3.2825 volts. And since they are connected in parallel, they are always equal. So the voltage in the 3 ohm resistor is also 3.825 volts. But we are looking for current. So the current is equal to V over R. It's equal to 3.825 all over 3 is equal to 1.275. So since we are using conventional currents, outside the battery, it would be from positive to the negative end. So this is the positive end. It should not be, the current drawing should not be like this, but it should be like that. Therefore, since it's pointing down, we assign a negative value to it. So let's call it I1. I1 is equal to negative 1.275 amps. So this is not what we're looking for yet. We're looking for Ix, which is equal to the algebraic sum of all of the currents passing through the certain resistor if only one of the 3 sources is present. So we can say that it's I1 plus I2 plus I3. Since we already saw the value for I1, we can now erase the previous solution. The next source that we are going to be using is the 10 volt battery. So we can redraw it like this. Simplifying, we get this. Now that we have the value for the equivalent resistance, now we are going to assign the currents. So since it's still the conventional way, the current is still going down. So I2 should have a negative sign. But first, let's calculate the total current, which is equal to 10 divided by 6.71, which is equal to 1.49 amps. Since the connection is in series, the current will always be equal. But this 1.71 ohm resistor is composed of two other resistors connected in parallel, namely the 4 ohm resistor and the 3 ohm resistor. To look for the current passing through the 3 ohm resistor only, we have to get the voltage across the two resistors or across the 1.71 ohm resistor since it is in parallel. So voltage is equal to I times R is equal to 1.49 times 1.71, which is equal to 2.55 volts. And since we already have the voltage, we can safely say that the voltage passing through the 3 ohm resistor is also 2.55 volts because it is connected in parallel. Now we look for I2, which is equal to voltage over resistance, 2.55 divided by 3, which is equal to 0.85 amps. But since we established earlier that the current is going down, we should add a negative sign. Therefore, we already have two currents. Now we are just going to look for the current passing through S2, or the only current source in the example circuit. Now we can redraw the whole circuit like this. With the current source over here. 4 amps. So since the current source is in parallel with all 3 resistors, we can safely redraw it with only one resistor. But how do we look for this? It's using Ohm's law, or using the properties of a series and parallel circuit. This is the formula. So the resistance will now be 1.28 ohms. This is still 4 amps. Now what we're going to do is we're going to look for the voltage passing through the whole circuit. So voltage is equal to IR, which is equal to 4 times 1.28, which is equal to 5.11 volts. So now we have 5.11 volts, and since all of the resistors are connected in parallel to the current source, and since the current source has the arrow, we have to follow that arrow, and it also points downward. So this is I3, and I3 is equal to the voltage over the resistance of the resistor, which is equal to 5.11 volts over 3 ohms, which is equal to 1.7 amperes. And since it's pointing down, we have to assign a negative symbol. So since we have all 3 currents already, we can now solve for the current passing through the 3 ohm resistor, or Ix. So we established earlier that Ix is equal to I1 plus I2 plus I3. Now, we just need to plug that in. And we get negative 3.825 amps. Now, why is it a negative? It doesn't mean that we have an incorrect current, but it just implies that the negative sign only implies that the current should go to the opposite direction. So, Ix is equal to 3.825 amps.